Well, good morning to everyone. Welcome to Department of Collegiate and Technical Education, Department of Mechanical Engineering. Course is Machine Design, 15ME53T, or 5th semester Mechanical Engineering. 4th unit, 6th session. Simple problems on flange coupling. Now, second problem. Design a protective type plane of cast iron flange coupling for a steel shaft transmitting 15 kW at 200 rpm and having an allowable shear stress of 40 megapascal. The working stress in the bolts should not exceed 30 megapascal. Assume that same material is used for the shaft and the key, and that the crushing stress is twice the value of this shear stress. The maximum torque is 25% greater than the full load torque. The shear stress for the cast iron is 14 megapascal. Students, read the problem another 2 times and list out the given data. Given data, it is a shaft transmitting a 15 kilowatt at 200 rpm. That is P is equal to 15 kilowatt and N is equal to 200 rpm. And having an allowable shear stress of 40 megapascal. It is allowable shear stress for shaft, bolt and key. And a working stress in bolts should not exceed 30 megapascal. The working stress in the bolts is 30 Newton per millimeter square. Assume that the material is used for shaft and key, and that the crushing stress is twice the value of its shear stress. That is, sigma c is equal to twice the tau of the shaft material, that is 80 Newton per millimeter square. Next is the maximum torque is equal to T mean plus 25% of T mean. Here, what we obtain from that, the maximum torque be transmitted, that is from the power transmission, that T is equal to average torque or the mean torque. While designing that one, we are going to use the maximum torque, that is the T mean plus 25% of the T mean, that is equal to T maximum is equal to T mean into 1.25. Now the cast iron, the allowable stress or the shear stress for the cast iron is 14 megapascal. Now let us start to design, that is a shaft, hub, flange, keys and a bolt. Now let us do one by one. Design of shaft. Let D, capital D is equal to diameter of a shaft. We know that the torque to be transmitted by the shaft, T is equal to 9.55 into 10 to the power 6 into P divided by N Newton millimeter. This is the T is obtained. We extracted this T from the power equation, power transmission equation, that is P is equal to 2 pi NT divided by 60 in watts. Similarly, 2 pi NT divided by 60,000 is a kilowatt. Now here, substitute the values of P and N here and calculate the T mean. What we obtained from the T torque here, this is the average or mean torque. Now consider the service factor while transmitting the maximum the torque, that is T maximum is equal to T mean, what we obtained from the above equation, plus 25%, that is 25 divided by 100 into T mean. Now after substituting the T mean in the above equation, and now finally we got that is maximum T maximum torque to be transmitted, that is equal to 895,312.5 Newton millimeter. Use this maximum torque to design the shaft. Now we are going to design the shaft on the basis of the pure torsion, that is the maximum torque to calculate the diameter of the shaft. The maximum torsional shear stress due to the torsion loading is given by tau is equal to 16T divided by pi dq Newton per millimeter square. Extract the diameter from the above equation and substitute the values here. that is equal to cube root of 16 into t divided by tau into 5 millimeter. Now substitute the values of T maximum and tau in the above equation and calculate the diameter of shaft. Now substitute the values of the T and the tau, allowable stress for the shaft material. Now finally we have that the 48.4873 millimeter. Now this is the diameter obtained from the mathematical relations in the torsion equation. Now next is select the standard diameter of shaft from the table. That is now here the standard diameters are available in these ratios in this series 6, 8, 10, 12, so on, 45, 50, 56 here. Now what the available diameter is lies between 45 and 50. Those available diameter, that is the standard diameter only 45 and the 50. Now let us choose that is the maximum the diameter, that is the 50 here. Now the shaft the standard diameter of the shaft is 50 millimeter. Design of hub. The usual proportion of hub used in practice is d1 is equal to the hub diameter is equal to 2 into d millimeter. Now the d1 is equal to 1 into 50, it is 100 millimeter, and L length of hub is equal to 1.5 into d, that is 1.5 into 50 is equal to 75 millimeter. Now let's show. Now here we have the usual proportions here. Usual proportions, that is proportions empirical rules. Substitute the values here, get a d1 outer diameter of the hub and length of the hub. Now let us check this. These dimensions are safe or not while considering the design of the hub as similar to that of the hollow shaft, and substitute all these values in that is the equations and check the individual shear stress. Now let us now check the individual shear stress in the hub. Torque transmitted by hub is equal to T is equal to pi by 16 d1 to the power of 4 minus d to the power of 4 divided by d into tau. Here this is the here we are going to assume as a the hub as a it is a hollow shaft. Now here we are going to extract the tau, the individual stress, from the equation. Now substitute the values of T maximum, d1 and d in the above equation and calculate the individual shear stress in the MUFF or the sleeve. Tau is equal to 16 into 895312.5 divided by this one, that is pi into 100 to the power 4 minus 50 to the power 4 divided by 5. Finally we got that is the tau is equal to 2.43, that is the individual shear stress in the hub material, that is assumed as a hollow the shaft. Since the individual shear stress in the hub, the cast iron, is less than the allowable shear stress of the hub, therefore the design of hub is safe under the given condition. Now the design of key. Once we fix the diameter of the shaft and inside diameter of the hub and outside diameter of the hub, the next step is to find out the design of the key here. Usually we are going to select the dimensions of the key respected to the diameter of the shaft. Now let us see in that we have the 50 millimeter diameter. Let us see that is the table to select the keys here. Now in this table, dimensions of the parallel keys and the keys are there in the page table number 4.1 in the page number 69. Here that for shaft diameters above and up to is there. However, the shaft is lies between 50 and the 58. Here two series are there, 40 and the 50, 50 and the 58. We are going to take that is the larger one, dimensions of the keys for the safety purposes, and then that is the width of the key B is equal to 16 millimeter and height of the key is equal to 10 millimeter. Now let us choose that this in this series. Now here that is the you find that for shaft 50 millimeter, width of the key is be 16 millimeter. Since the crushing stress for the key material is twice the shearing stress, therefore square key may be used. And the shear, when comparing the shear stress and crushing stress, and the crushing stress is twice that of the shear stress, in that case we are going to use it is the square the keys. Now the height of the key is equal to the width of the key, that is equal to 60 millimeter in case of the square key. Now once we know that is the fix the dimensions of the key, now let us check the individual stresses developed in the key while transmitting the torque. That is, it may failure in the form of a shearing and the crushing. We know that length of the key, we need to check, that is we need length of the key. The length of the key is equal to length of the hub, that is equal to 1.5 d, 1.5 into 1.5 times the diameter of the shaft, that is equal to 75 millimeter. Let us check the individual shear and the crushing stress in the key. First of all, let us consider shearing of the key. Shearing strength. You know the shearing strength, the T is equal to half into tau into B into D into L. Here substitute the values here and find out the individual shear stress here. Now the tau is equal to T into 2 divided by B into D into the L. B the width, D the diameter, and L is the length of the key. After substituting the values here, we get it is 29.84 the shear stress, individual shear stress in the shaft. Once and the second one, now considering the crushing strength of the key. Here the crushing strength is equal to T is equal to 1 by 4 into sigma B into H into D into L. Substitute that values here and find out the bearing pressure or the crushing strength of the individual crushing stress in the key material. That is, substitute the values here and calculate the bearing pressure or the crushing stress here, that is equal to 59.68. Now since the individual shear and crushing stresses are less than the allowable stress in the key, therefore the design of the key is safe under the given condition. Now let us move on to the next stage, is the design of the flange. The usual proportions of the flange used in practice are D1 is equal to the hub diameter 2 times the D, and D1 is equal to 100 millimeter, and D2 is equal to 3 times the diameter of the shaft, D2 is equal to 150 millimeter, and the outside diameter of the flange is equal to 4 times the diameter of the shaft, that is equal to 200 millimeter. Now the thickness of the flange from the empirical rule, that is T is equal to 0.35 into D plus 9 millimeter. We have got a 26.5 millimeter. Then we are going to round up into the next even number, that is thickness of the flange is equal to 28 millimeter. Now we have the dimensions of the flange, that is diameter of the board circle, outer diameter of the flange, and the thickness of the flange here. Now let us check the individual shear stress while transmitting the torque from one shaft to the another the shaft. Now the design of the flange. Torque capacity based on the shear of the flange. Here we have that the D1 is equal to 100 millimeter, D2 is equal to 150 millimeter, D3 is equal to 200 millimeter, and T is equal to 28 the flange thickness here. Now we apply, that is substitute the values here, that is the shearing strength of the flange. Now here the flange may failure at the junction of the hub and the flange. Okay. Now substitute the values in the above equation and calculate the individual shear stress. Now since the individual shear stress is less than the permissible shear stress in the flange, therefore the design of flange is safe under the given condition. Now the design of the bolt. Calculate the number of bolts required to the coupling with the empirical rule, that is high is equal to number of bolts, that is high is equal to 0.02 D plus 3. Substituting the values of D here, we have got a 4 number of bolts to fasten, that is the 2 flanges. Okay. Now D is equal to 150 millimeter, that is the diameter of the bolt circle, and T is equal to 28 the flange thickness. Now we can also calculate, that is the the diameter of the bolt with empirical formula, or you use that is the shearing strength of the bolt while transmitting the force. Better you calculate the that is determine the bolt diameter from the empirical formula and check whether the bolt is safe or not while calculating the induced shear stress in the bolt material. You can use both of the method also. Both are the correct. Okay. Now D, the empirical rule is D is equal to 0.423 D divided by square root of I, that is the number of bolts, plus 7.5 millimeter. After substituting that is the D and the high number of bolts, we have got a 18.05075 millimeter. From the table 9.8 in the design data handbook, the standard size of the bolt is equal to 20 millimeter, that is M20 bolt is used. Check the shear by considering the equation. Shear of the bolt by considering the equation. Determine the diameter of the bolt considering the torque capacity based on the shear of the bolt, that is equal to tau into pi into high d square d into d2 divided by 8. From the above equation we are going to extract the tau, that is individual shear stress. Substitute the values of 8 into the values of the t d square and high plus d2 and calculate the individual shear stress. Here we have got 9.49 Newton per millimeter square. Now since the individual shear stress is less than the permissible shear stress in the bolt, therefore design of bolt is safe under the given condition. Now that's all the design of, that is the flange couplings. Here we are going to first design the summary. Here first of all we are going to design the shaft diameter depends upon the transmitting the torque, the power and the RPM. Next we are going to use the empirical rules, determine the dimensions of hub, dimensions of the flange, dimensions of the bolt and number of bolts with empirical rules, and we are going to check the individual stress in the hub, individual stress in the flange material, individual stress in the bolt material. Once the individual stresses are less than the allowable stress, therefore the design is safe under the given condition.